All right, so I love talking about probability. It's my favorite topic. This has got to be one of my favorite lectures to do. So some of this is going to be review. You obviously took undergrad stats, so you should have covered this. If not, welcome to the world of probability. Let's look at some basic concepts. First, there's the event. The event is the outcome of interest. It's the outcome of a random experiment. An example of a random experiment would be something like flipping a coin, or your outcome could be heads or tails, rolling a fair die. You have six possible outcomes, one through six, right? Or I mean, if you roll two of them, you could have different outcomes as well. An individual's body mass index, an individual's height, all of those are examples of a random experiment. The events are elements of a sample space. So, for example, heads, flipping a coin is an event. The sample space for flipping a coin would be heads and tails. Rolling a fair die, you have six possible elements of the sample space. Rolling a six is one event, an outcome of an experiment. Excuse me. Body mass index for a sophomore male student. In a private university or college, that's another event. Okay, so those are examples of events. Those are outcomes of random experiments. Probability itself represents the proportion of times an event is expected to occur in the population. Okay, so what's the probability of landing the heads? There are two possible outcomes of a random experiment in the sample space, heads or tails. So the probability of heads would be, well, since there's two possible outcomes, it's one of the two, it's 0.5. What's the probability of rolling the six? So there are six possible outcomes to a random experiment in this case. So the probability of a six, and you'll see that I do PR for probability. And then in parentheses, we have six. Probability of six is one. One of the six possible outcomes are 1.6.167. So let's look at some properties of probability. Property one, these are extremely important for you to appropriate. Probabilities range from 0 to 1. That means it cannot be negative and they cannot be above 1. So let A be an event. The probability of A is greater than or equal to 0 or less than or equal to 1. Those are its boundaries. So if I were to ask you which of the following is or are not probabilities, the appropriate answer would be the negative value because it's below 0 and the value that's above 1. So it'd be B and C. So E would be the appropriate answer. Property number two is that the probabilities in sample space S, and we'll call sample space S just for sample space, of all possible events must add up to 1. So probability of the sample space is equal to 1. So this is regardless of whether we're dealing with a continuous or discrete variable, it's the same outcome. So imagine that four individuals are running a race, and we have data on past performance. Using these data, we compute the probability of each racer winning the race, and we get the following results. Looks like racer 3 has the greatest probability of winning the race, followed by racer 2, 1, and then 4. 4 would probably be me, right? What's the total probability of success in the sample space? Well, we just add all the probabilities together. Let's see what we have this, what we call a cumulative probability distribution, CDF, cumulative distribution function. And we add these all together, we add up to 1. It always is going to add up to 1. Property 3, the complement, and notice how I spell it, not compliment, like, oh, you look great today. Complement with an E of an event is the event not happening. Let A be an event in a sample space S. Let This is called not A be the complement of event A. So not A is the complement of event A. If the probability A is the probability of event A, the probability of the complement of A is 1 minus the probability of A. So probability of not A is 1 minus the probability of A. This comes in really, really handy. So what's the probability that racer 3 wins the race? It's 0.41. Let me just actually, I have all this stuff here for you. All right, let's continue here. Oh, I don't want to do that. Whoa, what am I doing here? All right. Yes, here's our problem. Okay, so we had probability that racer 3 wins the race is 0.41. The probability that racer 3 does not win the race, well, that's just it's a complement of the probability that x equals 3. So it's 1 minus the probability of x equals 3 or 0.59. The next question is, what is the probability that nobody wins the race? Well, somebody's going to win the race, so a complement of nobody winning the race is 1 minus somebody winning the race. So somebody's going to win the race. A complement of that would be probability, it would be 1 minus the probability of somebody winning the race, or 1 minus 1, which is equal to 0, right? 0. All right, let's continue on. Property 4, probabilities of disjoint events can be summed. Okay. If A and B are two disjoint is the same as saying they're mutually exclusive or complementary events, it means they cannot occur together. If the probability of A or B occurring is the probability of A union B. So we use this symbol, it's a U symbol, so it means the union of the two. It's synonymous with or, so probability of A or B occurring is the union of the two, and that's equal to the probability A plus probability of B. Using the data in table 1, what's the probability that either racer 4 or racer 2 wins the race? Well, racer 4 has a probability of 0.10 and racer 2 has a probability of 0.34. So they can't simultaneously win the race. So the probability of either of the two winning the race is 0.34 plus 0.10 or 0.44. So you should think of or as being synonymous with union, which is synonymous with addition when you work with probabilities. Okay. And I already mentioned cumulative probability, and I showed you how these accumulate to equal 1. But this is a handy notation that we use, which is kind of odd because it says what's the probability of x being less than equal to x? It's like, oh my God, what the heck are you talking about? Well, when we have the capital X, we mean a variable. It's just a generic variable. Less than or equal to x is a value on that variable. So like what's the probability the weight is less than or equal to 140 pounds? So the little x is a specific weight. Using the data in table 2, what's the probability that x is less than or equal to 3? So we use the idea of there being a cumulative probability. So we accumulate going from lower to higher, from left to right, the probability distribution. So we just add all these together. 40 plus 0.25 plus 0.2 is 0.85. Using the data in table 2, what's the probability that x is less than or equal to 2? So it'll be 0.4 plus 0.25 or 0.65. All right. Think about continuous random variables. There are no discrete values. Probability of a given outcome in a sample space is 0. That's because we can like define it to such a unique value that the probability is 0. So body mass index could be 17.64, 671, 359. It can get very, very precise. Because it's so precise, the probability of that value is 0. when we deal with probabilities with continuous variables, we don't, because of that, the issue of the probability being equal to zero for any individual point, what we instead is we look at the area under the curve. This is a curve, right? So the area under the curve is the area of that curve, basically, between two values. Like, for instance, we may say, what's the probability that one weighs between 160 and 170? Because we can calculate that. Unfortunately, we don't do it by adding like we did with discrete variables. Excuse me. Instead, we use calculus and integrate, do what we call a definite integral to find the area between two different points. So that's beyond the scope of this course. If you're interested, that's fun. But you don't really need it because in most distributions, we have tables available to help you find the probabilities. You don't have to use calculus to do that. Somebody else already did that. In terms of calculating probabilities, we can do so using the addition rule or the multiplication rule. We already kind of dealt with the addition rule when I talked about the probability of either of two disjoint / mutually exclusive events, right? So, but events aren't always disjoint. Sometimes they can co-occur. And when they do, we use the addition rule. So the probability of A or B is the probability of A plus the probability of B minus the probability of their joint occurrence, because that can happen. So the probability of A or B is the probability of A plus the probability of B minus the probability of A and B co-occurring. So you can see this really well with this Venn diagram. But there's two separate probabilities. There's two separate outcomes, I should say, or events, right? Remember, events are outcomes of a random experiment. You could either get A or B, but in this case, you can get both A and B. And this little area here represents the co-occurrence of A and B. So, excuse me, using the addition rule, as we did when we had two disjoint events, we just added the probability of A to the probability of B, right? But because we're doing that and they can co-occur, we would be double counting. So we subtract one of those, that little football shape area. We subtract it from the calculation. So that's why we do the probability minus the probability of A and B. We just want to avoid double counting. Okay. If A and B are complementary events, what's the probability of the intersection of A and B? Well, in that case, if they're complementary, so they cannot co-occur, that would be just the probability of A plus the probability of B, because there would be no overlap. So that would be zero. Okay. Let's do a little example here. Here's the pet example. What's the probability of cat ownership? Well, it's 0.35. So let A equal cat ownership and let B equal dog ownership. So the probability of cat ownership is 0.35. The probability of dog ownership is 0.30. And the probability that somebody owns a dog and a cat, and we use this inverted U to mean the intersection, is 0.15. So what's the probability that one owns a cat or a dog? Well, in this case, we can add them together, but we have to subtract the probability of their joint occurrence because they do co-occur. We got 0.5. Independence occurs in certain cases if the probability of A times the probability of B is equal to the probability of A intersection B. The two events are considered independent, and we'll see why that occurs shortly. So the one question is dog ownership independent of cat ownership? Well, let's see. The probability that one owns a cat times the probability that one owns a dog is 0.105. Probability that one owns both is 0.15. These two are not equal, so therefore they are not independent. We'll talk again more about that shortly. Let's look at reading it. So this is just a great introduction into probabilities. And we get a lot of probabilities from reading what we call cross-tabulation tables. These are tables where we have two variables. And in this case, both variables are binary or have two different levels. Like, for instance, here's a question about snow sports. Did you participate in a snow sport last winter, such as skiing or snowboarding? You can have yes or no. Okay. Like 70 did and 930 didn't. Did you mountain bike at a ski area last summer? Yes or no? All right. So we had 140 who did and 860 who didn't. So these tend to co-occur because a lot of ski areas have mountain biking areas too. All right, let's talk about these different types of probabilities that we can gather from a cross-tabulation table. First of all, we have marginal probabilities. Those are the probabilities of one of the two variables, a value or an outcome of one of the two variables, ignoring the other variable. Like, for instance, the probability of mountain biking last summer is 140 out of 1,000. So when I do that, I ignore the fact that some people participated in a sport and others did not. So that's irrelevant when I'm looking at the probability of mountain biking. Okay, that's called a marginal probability. What's the probability of participating in a snow sport? Well, let's see, 70 people did out of 1,000, so it'd be 70 divided by 1,000, or 0.07. So those are marginal probabilities. Let's look at conditional probabilities. So conditional probabilities are probabilities conditioned on the occurrence of something else. So for instance, the current event A influences the probability of event B. So I might ask, like, what's the probability of B given A, right? So this is the conditional probability of B given that A has occurred. By definition, the probability of B given A is the probability of A intersection B divided by the probability of A. Okay? We can play around with this a lot to solve many different problems because we just rearrange this equation. But there's a stipulation here. The probability of A must be greater than 0 because we can't divide by 0. Let's go to the last pet example. What's the probability that one owns a dog given one owns a cat? Well, that's the probability that one owns a dog and a cat divided by the probability that one owns a cat. We have all these probabilities here, so we get the conditional probability of owning a dog given one owns a cat is 0.429. So, and we can trace back to where we were before, like we can get the probability of owning a dog and a cat just by doing a little algebra here, right? So if we multiply both sides by the probability, well, if we multiply both sides by I should say in this case, I want to isolate the probability of dog ownership and cat ownership. So I would multiply both sides by the probability of cat ownership. That would eliminate this denominator here and put it out here. So that's what we get, right? Just rearrange it so we get 0.429 times 0.435 or 0.15. And that's what we had before, right? Somewhere here. Yeah, here. Okay. That's it. Right. All right. So using the data in table 1, what's the probability of participating in a snow sport given one mountain bikes? Now, using the table, there's two ways we can do this. We can do it using the equation, but we can also use the table. So if I want to know what's the probability of participating in a snow sport condition on mountain biking, so first thing I would do is I would restrict my sample to those who mountain bike. There was 140 people, right? Now, of those 140, 45 participated in a snow sport. And the question was, what's the probability of participating in a snow sport given one mountain bike? So I have 45 divided by 140 or 0.321. So what I did was it's like I created a new sample just out of those who mountain biked last year. Okay. Using the data in table 1, what's the probability of not mountain biking given one participated in a snow sport? Well, you participated in a snow sport. Did you? Yes. Not mountain biking will be 25 out of 70 because our sample is restricted to the 70 people who participated in a snow sport. So the condition is after the slash, okay? Look at the general multiplication rule. The general multiplication rule is the probability of the intersection of A and B. Excuse me 1 second. All right, sorry about that. There's a phone call I had to answer. People don't know I'm online. So that's interesting about this general multiplication rule and why we talked about the independence issue before. So remember we stated that if the probability of A intersection B is equal to the probability of A times the probability of B, we have independence. And the reason is that if A is independent of B, the occurrence of A will provide no information about the occurrence of B. So when something's conditional, the occurrence of whatever's behind what behind the slash here will give us some information about the occurrence of B. Like knowing that A occurred will tell me something about whether or not B occurred. But if the occurrence of A tells me absolutely nothing about B, we could just pretty much ignore that A. So that's how we got that independence equation. Okay, so and an intersection are synonymous, and intersection and multiplication are synonymous. So you can always think about multiplication being associated with and, addition with or. What's the probability of participating in a snow sport and mountain biking? Well, actually, I probably did that here. Snow sport and mountain biking. Let's see. Let's find where I have that. Snow sport and mountain biking. So, well, I can just go directly to the table and do this, to be honest. Right? I can do it two different ways. So I can do it either through the table or through the equation. So using the equation, it would be the probability. So again, we're dealing with that multiplication rule. We're just rearranging the equation. So it equals I don't know, I have two probabilities here. Probability of participating in snow sport and mountain biking is equal to the probability of snow sport given mountain biking times the probability of mountain biking. And then using the table, I can just figure that out, right? I have to know all the different definitions, basically, like what's a conditional probability. So this is condition on mountain biking, and then what's a marginal probability here. But I can also go directly to the table. So on exams, I could ask you to do either or, right? Use the table or, do it with the equation. So, but let me show you in a table, if I wanted to know the probability of participating in a snow sport and mountain biking, it would be the intersection of the two. So did you mountain bike? Yes. Did you participate in a snow sport? Yes. So they intersect at 45. So 45 out of 1,000 people did both. So my answer would be 45 divided by 1,000 or 0.045. Okay, there it is. What's the probability of participating in a snow sport and not mountain biking? Well, then we go back here and hopefully I did it. Snow sport and not mountain biking. Did I do it here? Yeah, this is maybe or maybe not. But if I wanted to solve, I don't think I did it here. It says here probability mountain, blah, blah, blah. Did I do? I didn't. I don't think I did it. But if I wanted to do that, I would have to go. What's the probability of participating in snow sport and not mountain biking? So you participated in a snow sport, yes, and you didn't mountain bike. That's 25 out of 1,000. 25 out of 1,000. Oh, I did it. Okay, right here, 0.025. So either or, you could either just do 25 divided by 1,000, or you can use the multiplication rule and do the calculation. So again, it's either or depending on what someone asks. And the question is, why would you do that? Because you don't always have a table, right? But you may have the probabilities. So if you have the probabilities and you don't have the table, you can just use the probabilities to do the calculation. But if you have the table, and it's easy to just look for the intersection of the two. But in this case, we use the multiplication rule here to figure it out. Okay? So we have the probability of participating in snow sport, that's 70 out of 1,000 folks. Probability not mountain biking given one participated in a snow sport is 25 over 70. So the probability of participating in a snow sport and not mountain biking is the product of the two. Okay. The total probability rule is an interesting probability. So this is the same as a marginal probability. The only reason I show it to you here is because we use it as our denominator of Bayes' equation, right? So it makes sense, but the probability of an event A is the intersection, is the sum of two separate intersections. So it's the probability of A. So we're just saying, what's the total probability A? A can occur with B or A can occur without B, right? So if we look at this Venn diagram, we see A is this blue circle. So you have this part of A that occurs by itself without B. That's the probability of A intersection with not B. That's this little area here to the left, plus the probability of A intersection B. That's this little area here where they intersect. That's just the total probability of A. Sounds kind of stupid, doesn't it? But it's not. We need it for the denominator of our Bayes' equation. Okay? And again, you can figure it out by running through a table or by just using the calculation using the equation. So you have probability of participating in snow sports, so that's probability of mountain biking and participating in the snow sport plus probability of not mountain biking and participating in the snow sport, because those who participate in snow sport either mountain bike or they don't, right? So that's why we divided it as we did. Okay. Let's talk about screening tests, my favorite thing. If you took epi with me, which everybody did, I believe, you know how to do this. So this should be just a quick review here. So prevalence is the probability of having the disease in the population. False positive is testing positive when one does not have the disease. And a true positive is testing positive when one is disease positive. And a true negative would be testing negative, one is true negative. Sensitivity refers to the probability of testing positive given one is disease positive. Specificity refers to the probability of testing negative given one is disease negative. And again, these are conditional probabilities. So you can see that through the equation. You should remember them through the equation. So table 4 presents cross-tabulation of disease status and screening test results. As you know, I like to have you guys complete tables like this one, which you can do, right? So using table 4 and your knowledge of probability rules, calculate the sensitivity, the specificity, and the probability of a false positive result. Let's see if I did that. It looks like I did. Right, so sensitivity. I think this is what I wanted. Let's see. No, sensitivity is, so let's go back here. Sensitivity would be 1850 out of 2000. Specificity would be 40,800 over 48,000. So that's what I did here, right? And then what else did I ask for? I said false positive probability. Let's see what else I asked for. And the probability of false positive, that would be just 1 minus the specificity, because see, here's specificity refers to essentially the true negatives, and a complement of the true negatives is a false positive, because these are both part of the sample space for disease negatives, because either you can test positive and be disease negative or test negative and be disease negative, so they're complementary events. Okay. So it seems like I calculated the PPV here, but we'll get to that later. What else did I ask for? Complete the table. Okay, so you can complete this table here. So you should be able to do that, and you should remember how to do this. So if I give you the prevalence in this case is 4%. So if we multiply 4% by 90,000, we get the number of disease positives. So prevalence is just a probability of one having the disease in the community. So if I had like 100 people and it's 4%, 4 out of those 100 people are likely to have the disease. So it doesn't matter. As long as we have the prevalence, we can apply it to any sample. So that's what we're doing here, right? So if you wanted to complete this table, you would have this. I think this is it. Let's see. Is it 15? Let me sure I have the right one here. No, that's not it. Let's get to the right one. Yeah, right here. Okay. That'll be your result. And you can complete it. Really, you start with the prevalence and then work your way to using sensitivity and using the specificity to fill out the remainder of the table. Bayes theorem. Bayes theorem is a theorem that's a conditional probability. It's used to calculate, you know, events when we have some information, some prior information. Like B is some prior information. What's the probability of A occurring B, given that B has already occurred, right? So we have some prior information here. Like we have information about the sensitivity and the specificity of a disease we use it for calculating what we call a positive predictive value. So the PPV is just a play on Bayes' equation. So Bayes' equation is the probability of A given B. So it's just you have a conditional probability here, and we just went through this whole idea with the multiplication rule, etc. But you notice that the denominator is the total probability of B, so we divide it into A intersection B and not A intersection B, right? Right. So what we're doing is we're prepping for this situation. So what's the probability of having a disease given one test positive for the disease? So then instead of using A and B here, we have something more concrete, right? Testing positive and being disease positive, etc. Right? If we break this equation down, so the breakdown of this equation is using the multiplication rule, right? So we're doing it for each of these circumstances here. That's why you have this particular breakdown. Really beautiful. And this is why we need the total probability rule. So here we're going to have, well, let's talk about what's the probability of PPV, is the probability of being disease positive given what you test positive, right? So by definition, we have, well, this is the sensitivity, testing positive given one is disease positive times the prevalence, and the total probability of testing positive encompasses testing positive and being disease positive, or testing positive and being disease negative, or means addition. So if we translate this into those specific terms, this is sensitivity, this is prevalence, right? This is, well, probability of testing positive given one's disease negative, that's a false positive probability. And 1 minus the prevalence is, well, that's 1 minus the prevalence. That's the probability of being disease negative, okay? So we can use that to calculate PPV. We can also calculate PPV directly from a table if we wanted to. It's really important that you know how to do both and that you pay attention for when you're asked to do this. So it says here, using the data in table 6 and Bayes' theorem, calculate PPV. Let's see how that's done. Hopefully I did it here. Okay. So PPV, let me make sure this is the right equation. So PPV here, in this case, so it's the probability of being disease positive given one test positive. Again, let me make sure this is the right one. 10,000. Let's see, let me get to the right one. I don't believe I have that, but I can just talk you through. I'll talk you through that. Well, let's just do it here. Okay. If I wanted to know the PPV, the positive predictive value for this distribution here, given that it's the probability of being disease positive given one test positive, so the condition is testing positive, So we know that 16,290 people tested positive, and of those, 3,330 were disease positive. So we're saying, what's the probability of being disease positive given one test positive? It would be 3,330 divided by 16,290. Okay, in this table right here. Okay. Let's see what I don't know where I got those from. Let's see. Let's see. 10,000. All right. So I'll just leave that because it doesn't really make sense. Using the data from table 6 and Bayes' theorem. So let's see if I have a good example from Bayes' theorem. Maybe I have one. Yes. Let's find one. Looks like, let me just see where this one's from. Yeah. Okay, so this is this problem. Okay. This is this problem here. Using the data in table 7 and Bayes' theorem, calculate the PPV. All right, so we know that the sensitivity here is 0.99, specificity is 0.95. We have 15,000 individuals, and our prevalence is 6%, 0.06. All right. So if I wanted to calculate the PPV from the table, it's a conditional probability. It's a probability of being disease positive given one test positive, 1,596 tested positive, and of those 891 were disease positive, so it'd be 891 divided by 1596. I don't know if I did that or not. Doesn't look like I did that here. All right. Using Bayes' equation. So what I need for Bayes' equation is to have the prevalence, which you have 0.06. I need the sensitivity, which in this case is 0.99, and specificity is 0.95. I can just plug those into the equation, right? So let's do that here. Increase the size of this. Okay. So here's our equation. This is the total probability of testing positive. So we have sensitivity, probability of testing positive given one is disease positive, times the probability of being disease positive, prevalence, 0.99 times 0.06, and the total probability of testing positive. You can test positive and be disease positive, or remember, plus and or addition and or are synonyms, or you can test positive and be disease negative. So we get 0.99 times 0.06. This is a repeat of the numerator, plus 0.05 times 0.94. 0.05 is one minus the specificity, or the probability of a false positive result. And this is 1 minus the prevalence. So 1 minus 0.06 is 0.94, and we get 0.558. Okay. So if this is the same, we should get the same as we did using the table. Make sure we got everything right here. So you get 891 divided by 1596. Right, so it's the same. 0.558. Yeah, so it's the same thing. All right, so that's our refresher on probability, or if you're new to probability, that's your intro to probability. Use probability everywhere. Please read up and get to know it. Thank you very much.